So one of the things that the ITU do is, well, they first came up with the idea of 5G, but the ITU, they tend not to deal in 4Gs and 5Gs. They've got different ways of referring to these things. So if you're going to speak to an ITU person, you'll hear them talk about IMT 2020 rather than 5G. Now, we in the industry have labeled IMT 2020 as the 5th generation. So IMT 2020, they've come up with this table, and this is a list of system attributes that qualifies a technology to be referred to as IMT 2020 or as 5G. So we're looking at peak data rates of 20 gig downlink, 10 gig uplink, cell spectral efficiency. So whenever you talk about spectral efficiency, and again, we're not going to worry too much about this because it's radio stuff, but it's modulation, coding, it's antennas, that kind of stuff. So it's got to be a bit better than LTE released. We would quite like the latency to be better as well. That was one of the limitations of LTE, actually, is the fact that it was nigh on impossible to get down to or below about 2 milliseconds of sort of radio access latency. So there's a complete restructuring of the radio interface to allow that. User plane reliability in the order of sort of 5 nines or so. Connection density is a big problem as well. So 1 million things connected per square kilometre. And that's a lot of things. I mean, if you can imagine how big a square kilometre is, I mean, just look out the office window, you can probably see more than a square kilometre. But 1 million things in there connected. And of course, they're not smartphones. They're not all of them smartphones. There might be 1,000 smartphones per square kilometre, but the rest of the things will be pollution sensors and vehicles and sensors in the road. But that's a lot of things to connect. And that, of course, creates a problem for the user plane because that may be a lot of traffic, but it causes a bigger problem for the control plane. Because if I've got 1 million things that need to connect to base stations, possibly not just one base station, then you've got to go through a control plane handshake. So you got to wake up, you've got to register, you've got to be authenticated, and then you can maybe start asking what it was that you wanted to do. So it may turn out that all you've got, if you're a machine type communication device or chipset, it may turn out that all you wanted to do was transmit 10 bits of information, yet you had to spend 10 different handshaking messages to do that. So the control plane is an issue. So to get to these orders of connection density, we've got to address multiple things, really. One of them clearly is the control plane efficiency, so the messaging structure that we would use. But another part is maybe we need a different radio channel or a different style of radio interface to support very, very high connection densities. 10 to 15 year battery life, how do we feel about that? Well, of course, everybody wants it. You can have a 10 to 15 year battery life if you only move 200 bytes of data per day. Clearly, it's not for your smartphone, this kind of a thing. This is going to be for the remote agricultural sensor. It's buried in the soil. Once you've buried it in the soil, you don't really want to go back to it for quite a long time. It's going to wake up periodically, transmit a bunch of data about soil conditions and atmospheric conditions, and go back to sleep again. So 10 to 15 years, maybe. A lot of that has got to do with power efficiency. How efficient can the chipset be? But it's got a lot to do as well with the evolution of battery technology. Yeah, we want to be able to go fast, 500 kilometers an hour, and maximize efficiency. Of course we do. Now, the thing is, this is a lovely long list of clever things that we want the network to do. But surely it can't be applicable to every possible use case. There are only certain things that need 20 gigabits per second or 0.5 millisecond latencies. So having come up with a list of nice performance targets that we would like the 5G network to do, what we then have to do is to map it to the various use cases. So for example, where we have mobile broadband, those are the key performance indicators that are probably most appropriate. It's not a very strict mapping here. You might say, well, you probably don't need 20 gigabits per second. And, maybe I'm not that fussed about the overall efficiency of things and so on. But, these categories of service or categories of performance indicator are more appropriate to the mobile broadband use case. For machine type communications or massive machine type communication, you can see the focus is a little different. So now we perhaps are worried about, the communication or connection density and things like battery life in some cases. And there's the ultra reliable low latency case. So, we're interested in cell spectral efficiency, but the other thing we're interested in is the overall latency. So, you kind of get the idea here that, different service categories or use cases need to be mapped to different performance values. So the end result of all of that is that we've got to build a network that can do all of these things at various levels. And that's what leads to some of the inherent complexity of the network. And leads to an extent, I suppose, to the description of network slicing. At some point, it then just kind of becomes impossible to build a single network that can efficiently manage a very, very large and diverse range of services. So what you might as well do is to build one big virtual network and then host inside of that network a bunch of other networks. And then you can build those virtual networks inside your network with a set of properties suitable to support that use case. When we talk about network slicing later on, often the examples that we give is that we have a network slice for mobile broadband. We would have another network slice for machine type communications and so on. So they effectively become virtual networks within your network, and we can attribute each of those virtual instances of network with their own set of performance capabilities. And that should work on an end-to-end basis. So, whatever the end service is that you're communicating with. So if it was, let's say you're a vehicle company, so that means all of the Toyotas out there in the mobile environment need to be connected back to a Toyota back end somewhere with a network in between. That should probably include the connectivity at the back end of the network to the Toyota servers, and all the way down through and including the radio transport network, the base station itself, the radio interface, and the mobile device. So whatever that thing is sitting in the vehicle, the modem, the network slice should encompass the whole thing. So when we talk about determining what the network attributes are for a network slice, we tend to think of the core network and, okay, how many servers and how many computation, CPUs do we need, how much memory, and how do we connect all of these things together? Well, at some point as well, we probably need to include the device at the far end of the network. What services need to be included on the device? And that may well become a management object as part of the network slice. At some point in the, shall we say, in the early configuration stages of a service, when the chipset first logs on to the network, it will be assigned to a network slice. And then that network slice will then tell that chipset the manner in which it should behave to service the data flow for that particular network slice.